Hello, everyone. What I want to talk about now are dyadic intervals, and we're going to use them to describe and talk about the Hardy-Littlewood maximal function and the Lebesgue differentiation theorem, which in turn are going to be used to describe what's called the Calderon-Zygmund decomposition of an L1 function at height lambda. That'll be done in the next video. And that really is the main tool for proving that the Hardy-Littlewood maximal function, that is the main tool for proving that the Hilbert transform is weak type 1,1. The Calderon-Zygmund decomposition is that main tool to prove that the Hilbert transform is weak type 1,1. Okay, so what are dyadic intervals? And I want to make clear that I'm going to stick to the real line for these next two videos, but everything I do here works in higher dimensions. In particular, there are higher dimensional analogs of dyadic intervals. We're just sticking to the real line to make things go a little faster and to just make things a little smoother. That's really all. It's kind of like in 510A, we do measure theory in the real line, just not because measure theory in higher dimensions is particularly hard, but it just makes things a little smoother. It just, it removes some of the annoying technicalities and it gets to the heart of the matter quicker. Okay, so dyadic intervals are simply intervals of this form here for L and K integers. So we often like to isolate dyadic intervals of length 1 over 2 to the k, and those are just denoted by dk. So let me draw a picture to kind of illustrate what's going on here. All right, so let's get on to the whiteboard. Let's make this nice and big. Okay, so let's start off with, so first of all, let me write down the general form of a dyadic interval. So it's half open, half closed, so that each script dk partitions the real line. In particular, these are disjoints. So we're looking at intervals of this form, L over 2 to the k. Okay, so let's start off with k equals -1. Right. So we got these intervals here. All right. So when k equals -1, this is just 2 to the, well, it's just 2 to the -1. Okay, so obviously if we bring this upstairs, this is really just going to be 2, let's do that. So it's just going to be 2 times L minus 1 to 2L for L all integers. Okay. So in particular, script D -1 is all integers of this form. So when L equals 1, we have, let's say here, 0 to 2, L equals 2, 2 to 4, et cetera, et cetera. And really it's, half open, half closed, but I mean, whatever. That's not a real issue here. Okay, so -2, -4. Okay, so what happens when we have k equals 0? Okay. So I should say we have this for all k. Well, when k equals 0, so remember, it's L minus 1 over 2 to the k, L over 2 to the k. So when k equals 0, that's just, well, 2 to the 0 is 1, so this all goes away. So this is just going to be 0 to 1, 2, 3, 4, etc., etc. So this is 0 minus 1, sorry, positive 1, sorry about that. Minus 1, minus 2, minus 3, minus 4, minus 5. So maybe put this in red. Okay. And right, let's do one more. It'll be a little tough to fit, but I think I should be okay. K is minus 1. So you'll notice here, well, let's do one more before I say anything else. Okay, so yeah, again, in general, it's 2 dividing by 2 to the k. So when k is, sorry, I want plus 1. I already did minus 1. So, right, when k equals 1, this is all intervals of the form L minus 1 over 2, L over 2, as L varies over all the integers. Okay, so we get 0, 1/2. I'm not going to write all these, but you get the point. Well, I guess I'll write all of them, but not label everything. So, yeah, so you'll notice that we have very nice nesting properties, and we'll make that more clear in a second. So it's 1/2, 1, 3 over 2, 4 over 2, etc., etc. Minus 1/2 when L is minus 1 would give you, sorry, when L is 0, you get minus 1/2 to 0. Right, so L is minus 2, or L is minus 1 rather, minus 1 to minus 1/2, etc., etc. Yeah, so you'll notice that there's this nice kind of nesting property that at each level, each of these intervals is contained in a unique one, that kind of unique higher level. So we have this, or we could have done, doesn't really matter. Let's do this one here. This is contained in 1 to 2. I'll do it. This one is contained in 0 to 2, etc., etc. So we have this kind of peculiar nesting property, which we'll make clear. So this is the picture, and yeah, and of course, point is that we kind of, this picture just never really ends. We're doing this kind of picture, this partition of the real line for each k. Okay. Okay, so let's go back. Okay, so let's prove some properties. Well, one, as I mentioned, for each fixed k, dk, script dk partitions the real line, and that's really nothing to say there. Just this is trivially a partition of the real line for each fixed k. Okay, so let's make what I just alluded to with this nesting property more precise. Now let's prove it carefully. So for each dyadic interval, there exists a dyadic interval containing I, what's called I tilde, and we call this the parent of I. And the parent of I has a property that it contains I tilde being the parent of I, and the length of I tilde is 2 times the length of I. So, right, in particular, let's go back to this picture here. So this 0 to 2 is a parent of 1 to 2. 1 to 2 is the parent of 3/2 2. And you'll notice that each dyadic interval has 2 children. Okay. So this 0 to 2 has 2 children, 0 to 1, 1 to 2. So this is kind of like, asexual reproduction, but, which obviously does happen in biology. But anyway, I guess it just makes sense to call it parents, children, et cetera, et cetera. Yeah, so 0 to 1 has these 2 children here, 0 to 1/2, 1/2 to 1. 1 to 2 has these children here, 1 to 3/2, 3/2 to 2. Okay, so yeah, let's make that yellow too. Okay, so right, so let's prove this. The proof is pretty easy, but it's it's good to just play around with the definition rather than pictures, and yeah. So before I do that, let's introduce 2 more properties. So well, for any 2 rather dyadic intervals. So here, right, so here I and J are dyadic intervals. Well, the intersection is either empty, I, or J. So in other words, we usually state this as, for any 2 dyadic intervals, they're either disjoint or one is contained in the other. Okay? And also, if I is contained in J, then I is strictly contained in J if and only if J is the kth generation, or rather, if and only if J is the kth generation child of I for some I, or sorry, not for some I, for some K. Okay. Right. Right. So yeah, so the only way to have J larger, strictly larger than I, is if J is the kth generation parent of I. I think I said kth generation child. I meant kth generation parent. And what does that mean? So that just means here, basically what is kind of the obvious thing. So the 0th generation parent of I is just I. And inductively, kth generation parent of I is, well, take the k-1 generation parent and take the parent of that. Okay. So in particular, it's instructive to see what the 1st generation parent is, and that's just the parent. By definition, it's the parent of I0. I0 is I, so it's just the parent of I. So we just keep taking parents of parents of parents. All right. So this is getting a little crowded, so let me get rid of this. And yeah, if you look at our picture here, this makes perfect sense, really. just want to give, just some examples here with our picture. See, if you end up going anywhere or encountering any kind of dyadic anything, pictures really, really help in understanding. They don't prove anything, but they really help in understanding what is going on. So, right, let's go here and let me get rid of some of these colors here. Well, I guess already done there. Whoops, let's go to black here. So these colors are a bit distracting. So you make them black again. Okay, well, we can actually just look at this here. Right. So, let's take, take any two dyadic intervals. I don't know, let's look at 4 to 6. Let's look at 5 to 6. Let's look at this one. Let's look at this one here. Right? So this one and this one have no intersection. This one and this one do have an intersection, and the intersection is exactly this one here. Same thing, this one and this one do have intersection. It is 5 to 6. Right. On the other hand, this one and this one, they have intersection. It's exactly this one here. So just playing around, you can see it makes perfect sense that two dyadic intervals, let's take this one, oops, this one to this one, two dyadic intervals are either disjoint or one's contained in the other. That's basically just, pictorially, that's from this nesting property, okay? All right, well, let's look at just these blue ones. Actually, didn't have to get rid of any of the blue, but whatever. So, so you'll notice that, 0 to 2 is bigger than 3/2 to 2, obviously. And 0 to 2 is the second generation parent of 3/2 to 2. It is the parent of the parent. It's the grandparent. The parent of 3/2 to 2 is 1 to 2. The parent of 1 to 2 is 0 to 2. Okay? And we're just saying that has to happen. In order for one dyadic interval to be strictly larger than another one, that larger dyadic interval has to be the kth generation parent for some k. In this blue example, 0 to 2, 3/2 to 2, k is 2. It's the grandparent, the parent of the parent. Okay, so, right. 3 is going to be for homework. And now let's prove a very important, or let's introduce a very important property of dyadic intervals, which is really the consequence of 4 is more important per se than 4. So if you have any interval whatsoever, I, A to B, for A and B, real numbers, A is less than B. Neither A nor B are infinity. Now let's say L of I, the length of I, is B minus A. And let's say we have an integer k, and there is a unique integer k where this is true. 2 to the minus k minus 1 is less than or equal to the length of I is less than 2 to the minus k. Then I claim that the number of dyadic intervals of length 1 over 2 to the k that intersect I is at most 2. Okay, so let's prove these facts. And like I said, one is fairly obvious. There's not a whole lot to it. Intervals of this form for fixed k, obviously partition real line as L varies from integer to integer. So let's prove 2. And the proof of 2 is, well, let's just write a generic dyadic interval. Okay. So what we're going to do is divide L minus 1 by 2. So divide the top and bottom by 2. Okay. Which will give us the following. Okay. So let's say L is even. So we need 2 cases, L is even and L is odd, and I will draw these 2 cases when we're done with the proof of 2. Okay, so if L is even, L over 2 is an integer, okay? But L over 2, L minus 1 whole thing over 2 is not an integer, but that's okay. This interval here, well, let's enlarge it to the left to get an integer on top. So we're going to the left by 1/2 over 2 to the k minus 1, okay, to give us L over 2 minus 1 over 2 to the k minus 1. Now, both of these numbers here are integers. L over 2 is an integer. Subtract 1, you get an integer. As I mentioned, L is even, so this is an integer. Okay. And this is going to be the parent. This is a dyadic interval strictly larger than I. And you can easily check that the length of I tilde is going to be 1 over 2 to the k minus 1, and that is 2 over 2 to the k. Well, the length of I is 1 over 2 to the k, so it's 2 times the length of I. Okay. Now, if L is odd, we basically do the same thing, except here we're going to leave this alone because L minus 1 is even, divide by 2 is an integer. So instead we're going to, in the numerator, add 1/2 to get a larger interval. And now both of these are integers. Right, so this is an integer here. This is an integer here. Okay, and of course this equals L minus 1 over 2 plus 1. Okay, so we're really adding 1 to this integer. So this is a dyadic interval. It's an integer, integer plus 1. Well, I think it's really, integer minus 1 integer, same thing. And again, same analysis here. The length of I tilde is 2 times the length of I. Okay. So in other words, to get the parent of a dyadic interval, if L is even, we have to include the left kind of sibling, if you will. And we include the right sibling if L is odd. So let's just quickly see that in action. All right. So let's go to the whiteboard. So I'll do a new whiteboard here. So yeah, let's just do k equals 0. So k equals 0, it's minus 1, 0, 1, etc., etc. Let's go to k equals 1. So 0, 1/2, 1, minus 1/2, minus 1, etc., etc. Okay, so let's say L equals, so remember we have these intervals. So let's do with k equals 1, let's look at the parent of that. So we're looking at intervals L minus 1 over 2 to L over 2. So let's look at L as, let's look at L equals 1. Okay, so L equals 1 is odd. So it's going to be 0 to 1/2. Okay, so right, so we by the proof to get the parent of this, we basically go to the right by 1/2. And we do that, we basically include the right sibling of 0 to 1/2, which is 1/2 1, to get 0 to 1. Okay. On the other hand, what does the proof tell us is the parent when L equals 2, which is 1/2 to 1? Well, L equals 2 is even. Okay, so the proof says, well, we include the left sibling to get the parent. That's 0 to 1/2. Okay. And so, yeah, the picture, is the proof corresponds with the picture. Okay. Right. All right. So let's get back to the proof. So 3 is going to be a fairly easy homework. I will give you a little hint for that, but yeah, 3 is not too bad. Let's prove 4. Okay, so remember what 4 says. If I is an interval with length b minus a, and we pick k where this is true, then the number of dyadic intervals of length 1 over 2 to the k that intersect I is at most 2. And it can be 1 or it can be 2. Let's just illustrate what's going on with the picture. So let's just, for simplicity, say k is 0. And I'll write down an interval where this is true. Okay, so let's look at dyadic intervals of length 1. So let's say I is something like let's say 0.1 to 0.9. Okay. So certainly k is going to be 0 if I is this interval here, because well, so 2 to the minus 0 minus 1 is 1/2, is less than or equal to 0.8. And it's certainly less than 2 to the minus 0, which is just 1. So yeah, k is 0 here. Okay. Now, if I take I and just shift it over a little bit, let's say to the left, you can shift it over to the right, not a problem. Basically, same effect. You shift it over to the left, we get that 2 dyadic intervals of length 1 intersect I. In particular, -1 to 0 and 0 to 1. Or we could have something like I is like here, in which case 0 to 1, 1 to 2 intersect I. Okay. And I think I mentioned also that this works for I, any other, half open, half closed, fully closed interval, doesn't matter. And lastly, 2 here doesn't matter. We could have 100 million here. What matters is we have something independent of k and independent of I. All right, so let's get to the proof of 4. And the proof is, the idea, the technique is called a volume count. here in one dimension, it's length. So it's a length count. And we're going to count things by looking at lengths, which is really interesting. I have a clever proof. I mean, it's a nice proof idea. Okay, so first of all, instead of all these j in script dk, where j intersects I is finite, if there's infinitely many of these j's that intersect I, then I is going to have infinite length. It doesn't, it has finite length. So let's say enumerate these as j1 to jm. Let's say this jl is al to bl. Let's say cl is in the intersection here. And let's say we're enumerating these intervals from left to right. Okay, so in particular, what I mean is, let's say A1 to B1 is the leftmost dyadic interval of length to 1 over 2 to the k that intersects I. So actually these will be adjacent. Doesn't really matter, but by connectivity of I, these will be adjacent. Yeah, so we're basically saying we have a situation like this here. So B1 is really A2. Anyway, so I guess I'll write this up here. Maybe I'll write the A1 up top. B2. And the last one, AM, BM. Okay. Whoops, meant to write this as BM on the bottom. But anyway, yeah, these intervals are left to right. Okay. So in other words, let's exactly write all this out. So in particular, C1 is in A1 and B1. Okay, so we have that here. B1 is less than or equal to A2. A2 is less than B2, et cetera, all the way to AM minus 1 is less than BM minus 1. BM minus 1 is less than or equal to AM. And CM is between AM and BM. Okay. So, right, nothing too subtle here. So we have CM here. Okay. Basically, all this is saying is what the picture is showing. Okay. Okay, well, so both C1 and CM are in particular in A to B. So this is A, this is B. We have C1, CM. So B minus A is bigger or equal to CM minus C1. Okay. But actually make this a little bigger. Okay, but CM is bigger or equal to BM minus 1. And C1 is less than A2. So you have CM minus C1 is bigger than BM minus 1 minus A2. Now let's compare this to a telescoping sum. So let's get rid of all this here. Okay, so B M minus 1 minus A2 is going to be B M minus 1 minus A M minus 1 plus A M minus 1 minus B M minus 2. See if I can squeeze this in. B M minus 2 minus A M minus 2. et cetera, et cetera. I'll write one more. Plus B, sorry, AM minus 2 plus BM minus 3. Okay, and we just keep going until we basically get B2 minus A2. Okay. Okay, so this is telescoping. All that is left is BM minus 1 and A2. But we can throw out some of the terms here. So in particular, well, this term here is bigger or equal to 0. This term here, bigger or equal to 0, et cetera, et cetera. So, so this quantity here is bigger or equal to just getting rid of those and keeping, so actually, I do want to keep those. So I want to get rid of this term here. Sorry, I did want to get rid of them. This term here, this term here. These kind of terms, we have different subscripts. They're all bigger or equal to 0. So in other words, what are we saying here? Well, let's keep this one. Let's keep this one. Let's keep this one, et cetera, et cetera. So this here is bigger or equal to keeping all the checked terms. And all the checked terms is this sum here. Okay. So this sum here is less than or equal to a telescoping series that telescopes and collapses to this right here, BM minus 1 minus A2. Okay, now we know what this is. This is the length of JL, which is 2 to the minus K. The sum has M minus 2 terms. Okay, so B minus A is bigger than M minus 2, 2 to the minus K. But 2 to the minus K is bigger than B minus A. That's how we picked K. That's bigger or equal to M minus 2 to the minus K. So all we do now is cancel 2 to the minus K's. So this becomes a 1 here. This is M minus 2. So M minus 2 is less than 3. M is less than 3, but M is a positive integer, so M has to be less than or equal to 2. And that completes the proof of 4. Okay. So I just want to comment on what 4 is really saying and what's really the importance of 4. Well, first of all, because intervals or dyadic intervals of length 1 over 2 to the K partition I, we can write I as this union here. L equals 1 to, let's do 2 here. And if M here is just 1, then these two dyadic intervals are just the same. That's fine. Okay. So we can write I as this union here. And actually, it's going to be a disjoint union. Okay. Or in other words, I is going to be a subset. I is contained in J1 union J2, where J1 and J2 basically have the same length of that I has. Instead of being the length of I, L over 2 is less than or equal to the length of I is less than L, because that's exactly how we picked, this is exactly how we picked K. So, you go back to 4, we picked K exactly in such a way that, remember, 2 to the minus K minus 1 is less than or equal to length of I is less than 2 to the minus K. But this here is equal to L over 2, the length of these intervals here, J1 and J2, is 2 to the minus K minus 1. We're picking these to be in dk. And this is exactly L. It's 2 to the minus K. So in other words, dyadic, there are, not all intervals are dyadic intervals, but we get the next best thing. We can pick at most two dyadic intervals where the union is containing I. The union is bigger than I, but these dyadic intervals have basically the same length of I. The length of I is between the length of these dyadic intervals over 2 and the length of these dyadic intervals. And this is what we're going to use in a moment. All right, so let's talk about the Hardy-Littlewood maximal function. Okay. 1 second. Okay, so what is a Hardy-Littlewood maximal function? Well, let's say f is an L1. Now let's define this function here as follows, and we'll see where this pops up when we prove the Lebesgue differentiation theorem, probably in the next video. Okay, so we're going to look at the supremum of all these integrals here. So we're basically looking at x. We're taking an R neighborhood about x, or an interval x minus r, x plus r, and we're basically taking the average of f on this interval. Okay. So I should mention that so mf of x is going to be, mf is going to take the real line to 0, and it could be infinity. There's no reason why this is not necessarily infinity. It might possibly be infinity. All we know, basically, and we get this for free, is that at least if f is an L infinity, then for the purposes of integration, this is less than or equal to the L infinity norm of f. Well, if we integrate that from x to the minus r, x plus r, we just get 2r, because it's a constant. So it's just 2r over 2r times the L infinity norm of f, which is the L infinity norm of f. And the conclusion is that this maximal operator, it should be called the maximal operator, but people call it the maximal function. Anyway, so this maximal operator, and it's sublinear, and this is probably the most important example of a sublinear operator other than f gets mapped to absolute value of f. This sublinear operator is bounded on L infinity. Trivially proved that. So if we can prove that it's weak type 1,1, then in fact we'll know that this is bounded on LP. by Marcinkiewicz interpolation theorem. And that's what I want to prove now. I want to prove that M is weak type 1, 1. Okay. Okay, so let's do that. Okay. And yeah, it's bounded for p between 1 and infinity, including infinity because we just proved that. Okay. It's not bounded for p equals 1, and in fact, I'll make this an easy homework. The maximal function, in fact, is never an L1 for any non-trivial, in other words, not 0 almost everywhere, f. So this is actually never an L1 for any non-trivial f. F is not equal to 0 almost everywhere. Okay, and that's actually pretty easy to prove, but so yeah, it miserably fails to be bounded on L1, but it is weak type 1, 1. So let's prove the theorem, and yeah, the proof of the theorem is probably just as important as the actual theorem. So we're going to do this in 2 steps. The first step is connecting this set here. So remember, we have to get an estimate for this set to prove that this is weak type 1, 1. And the goal is that this here is less than or equal to some constant times the L1 norm f over lambda for positive lambda. That's our goal. Okay. So I'm first going to connect this to a certain collection of dyadic intervals. Okay. And so I claim that this is a subset of the union of 2q, and I'll mention what that is in a second, where we're taking the union over all dyadic intervals q, where the average of f and modulus, an absolute value, over q is bigger than lambda over 4. So what does 2q mean? Well, that's just simply, let's say q is, let's say C for center, and let's say it has, well, okay, so, yeah, so let's say Q is the following interval. Yeah, so let's say this is what Q is. Okay, so here is the length of Q, and let's say this is whatever C is. Okay, so we can write this as basically a half open, half closed neighborhood. So this distance here is LQ over 2, LQ over 2. Okay, so in other words, Q is going to be the center minus LQ over 2, C plus LQ over 2. Okay. Make that a little clearer. So 2Q is the same interval, and this applies to any interval whatsoever, not necessarily just dyadic. Get rid of that. Okay. So if we write Q in this way, the center minus, well, the radius of the interval, essentially, which is the length over 2, to C plus the length over 2, then 2Q is the same interval with the same center, but twice the length. So it's going to be C minus LQ over C minus LQ, C plus LQ. So now the length of 2Q is twice that of the length of Q, but it has the same center. Okay, So in other words, right, so this big one here, let's get rid of this. So this whole thing here is 2q. Okay. And this distance here would be LQ over 2, LQ over 2. So this whole thing left to right, or this whole thing here is, the length of Q. This whole thing here is the length of Q. So the whole length is 2Q. Okay. 2 times the length of Q. Okay, so again, 2Q is the same as Q, same center, except twice the side length. Okay, so the proof is let's prove that the complement of the right-hand side is contained in the complement of my set here. So let's assume X is not in this union, and this is length. Sorry about that. Okay. So let's say I is an interval with length 2r and center x. These are the intervals we're looking at for the Hardy-Littlewood maximal function. Okay, so let's say JL are the at most 2 intervals, dyadic intervals, with length between 1/2 of the length of I and the length of I that intersect I. So I claim that none of these are in this script C, and script C is going to be the collection of I use dyadic cubes a lot, so if I say dyadic cube, I mean dyadic interval. And I should mention what are dyadic cubes. You literally just take the Cartesian product of all different dyadic intervals. You take the nth Cartesian product of all possible dyadic intervals to get dyadic cubes. So not very complicated. But let's say C is the collection of all these dyadic intervals. I claim that none of these are in C. Well, let's assume that one of them is in C. Okay. And let's say, remember, these are exactly the dyadic intervals that intersect I and that have length, it's between 1/2 the length of I and the length of I. Okay, so what does that mean? Well, then I claim that actually X is in this union, if this is the case. Okay. Well, let's see. We'll take X minus the center of JL. CL is the center of JL. Center of CL. Sorry, CL is the center of JL. Okay, so triangle inequality here. Okay, well, U is an I, so that's less than or equal to the length of I over 2, which is just R. Anyway, U is in JL, so that's less than or equal to the length of JL over 2. Well, right, so the length of, so remember that the length of I, let's go back here. So the length of I is less than the length of this these common lengths here. So the length of I over 2 is less than the length of J over 2 plus the length of J over 2, or rather the length of JL over 2 plus the length of JL over 2 gives you the length of JL. And actually it's strictly less than. Okay. So by definition of 2 times JL, that means X is in 2 times JL. And, well, we're assuming JL is in script C, so that means X is in this union here. So that means, well, the contradiction here is that, well, so that proves that JL cannot be in C. Okay. If it is, then we get a contradiction. Okay. There's really no contradiction here. This will always be true. If X is an I, and we pick JL in this way, then X will be in 2JL. We just proved that. So the contradiction is here. Okay. So JL is not in script C. So what does that mean? That means, well, it is a dyadic interval. So this has to be less than or equal to lambda over 4. Okay. Okay, so, right. So neither of these, so this means that neither of these are in script C. Okay, nothing special about L equals 1 or L equals 2, or even if there is just one of them. Neither of these are in script C. If any of them are in script C, then we proved that X is in this union, and we're assuming it's not. Okay, so let's put this all to good use. Okay, well, I is the disjoint union of these two, J1 or rather I is a subset of this disjoint union. All right. Well, so remember L of I is bigger or equal to, what was it, 1/2, well, it was 1/2 L, which L is the length of JL. Okay, so that means 1 over L of I is less than or equal to 2 over the length of JL. Okay, so yeah, so use this fact here, use this fact here, we get that this average is less than or equal to this sum, but neither of these intervals are in script C. And that means that this has to be less than or equal to, for both of these, lambda over 4. So we have a 2, lambda over 4, well, L goes from 1 to 2, so we get 2 times lambda over 4 is lambda. Okay? Now you'll notice that this is true for any R whatsoever. Okay? So in other words, lambda is an upper bound for all of, so basically what we've proven is that, forget about the soup here, for any R whatsoever, we just proved this is true. If X is not in this union. Okay. So if X is not in the union, then lambda is an upper bound for all of these averages for all R. The soup is the least upper bound. So the soup is less than or equal to lambda. Okay. So in other words, X is not in this set. The maximal function is this supremum. Okay. So we're done for this step. So the next step, okay, so right. So what have we done? We've, so let me get rid of all this here. So we've proven this step. So the next logical thing that we need to do is as follows. And what I do next, we're going to use in the next two videos, or we're going to use in the next two videos. This is going to be kind of the cornerstone of the Calderon-Zygmund decomposition. Okay, so get rid of this here. And this is going to illustrate why dyadic intervals are so useful. Okay, so the next step here is, well, I'm going to take the measure of both sides here. Okay, and the next step is going to be to prove that this is going to be actually, I think it's 8 times the L1 norm of f over lambda. Okay, so that's going to be step 2. Okay, so step 2 is proving exactly this. And remember, I said that the collection of all these dyadic cubes is script C. So this is really the union over all Q and script C of 2Q. Okay. All right, so let's prove this. And this is a really beautiful proof. Okay, so let's say Q is in script C. We already introduced the concept of the kth generation parent. Okay, so let's say the 0 generation parent again is Q, and let's say Q tilde 1, Q tilde 1 is the first generation parent, the parent of Q. Q tilde 2 is the parent of Q tilde 1, et cetera, et cetera. Okay. So whenever we take another generation parent, we increase the, we get 2 times the length of the child. So the length of the kth generation parent is 2k times the length of Q. Okay. So let's make a very trivial observation here. And this observation is really true regardless of whether Q is in script C or not. Okay. Well, obviously this integral here is less than or equal to integrating over the real line. I don't care how big the parent gets, it's contained in the real line, subset of the real line. This length here is equal to, well, 1 over it is 1 over 2 to the k times the length of Q. So for fixed Q, no matter how big, small, or in between Q is, when we let k go to infinity, well, it's this L1 norm of f, we're assuming f is an L1, over 2 to the k L of Q, Q is just Q, k has nothing to do with Q, and we let k go to plus infinity, this is 0. So what's the conclusion? Well, Q is in script C. We're assuming Q is in script C. But for large enough K, the kth generation parent is not in script C. So what that means is, for every Q in script C, there exists a natural number where the mth generation parent, or it could be 0, it could be 0. So it's not necessarily, m could definitely be 0, but the mth generation parent is in script C, but every larger generation is not in C. And you might grumble and say, well, how do you prove this? We really didn't prove it. Well, there's not a whole hell of a lot to this. You just take the minimum of all these non-negative numbers. Okay, so this set here is not empty. This set of non-negative integers is not empty. Okay, we just proved that for large enough k, the kth generation parent is not in script C. Okay, so you can always take the minimum of a non-empty subset of non-negative integers. That minimum always exists. Okay, so let's enumerate all these dyadic intervals. Okay, so in particular, let's call, let's get rid of this. Oops. Okay. So let's call this P. Okay. So let's enumerate all these Q tilde M, big M's satisfying this property, that they're some generation parent of something in script C, satisfying the property that any larger generation parent is not in script C. Okay. So we can write that as follows. It's a set of all P in script C where any larger generation is not in script C. And remember that we have P prime, any dyadic interval P prime is strictly bigger than P precisely if P prime is a kth generation parent of P. So this is also, you can write as the set of all P in script C that are maximal. Meaning, for any larger dyadic interval, P prime is not in script C. So this is script C. All right. And these are called Calderon-Zygmund intervals of my function f of height lambda. So these are very famous people in the modern study of Fourier analysis. So it's Calixto Calderon, Argentinian, and Antony Zygmund. You can look them up if you want more information on them, but they're the ones who came up with this Calderon-Zygmund decomposition that I'll talk about. Okay, so let's prove some properties about these Calderon-Zygmund intervals. And I should mention, well, any subset of dyadic intervals is countable because the set of all dyadic intervals is countable. So I claim that these are disjoint, and there's really not much to it. If P and P prime are two of these dyadic intervals, well, then either one is contained in the other or they're equal. Or rather, sorry, either one is contained in the other or they're disjoint. If one is contained in the other, then because both are in script C, so these intervals are all in script C, well, this would violate maximality. This is the collection of all dyadic intervals in script C where anything strictly larger is not in script C. So either these are disjoint or one is strictly larger than the other. Well, we can't have two elements in scripts, we can't have two of these elements where one is larger than the other. That's exactly the key property of these intervals. Okay, so that means they have to be disjoint. Okay. Okay, second, I claim that the length, if I add up all these lengths, I get 4 times the L1 norm of f over lambda. And this is a really beautiful, but this is really nice. This is really neat. Okay, why? Well, remember what it even means to be in script C. Okay. Remember, script C is the collection of all these intervals. Now, you might think, well, okay, script C, these are bad intervals because F has big average on these intervals. In some sense, that's true. But in another sense, because F has large average, that means the length of these are small. Why? Well, right, so just because QJ is in script C, that means this is true. So I'm going to multiply both sides by LQ of J. I'm going to divide by lambda, and I'm going to multiply by, let's multiply by 4. Okay. So this is going to get rid of this here, and this is going to be 4 over lambda. Okay, so what lives here? Well, this cancels this cancels this. So we get L of Qj, forget about a sum. L of Qj here is less than or equal to 4 over lambda times this integral here. Now let's sum up. The sum of the lengths is less than or equal to, pull out this constant, the sum over these QJs of absolute value of f. Well, these are disjoint. So when you take the sum over disjoint sets and you integrate, that's certainly less than or equal to integrating over the whole real line. That's 4 times the L1 norm of f over lambda. Okay, now let's finish up step 2. Okay, so let's look at this measure here. So we can't just take, we can't just say, well, this is countable, let's use countable subadditivity. We've got to be a little more careful than this. So remember that if Q is in script C, then Q is in one of these intervals for some J, okay? I mean, we proved that already. We proved that for every Q in script C, there exists a kth generation or an mth generation parent of Q, which we call P, and hence Q is contained in P, where P is in script C, but any further generation parent is not in script C. So everything in script C is contained in one of these Calderon-Zygmund intervals. Okay. So then the union of all this, if we increase the length, if we double the side length, is certainly less than or equal, or rather, this union here is certainly a subset of this union here, because Q is a subset of QJ. So if we increase the side length of both of these intervals, but keep the center the same, then 2Q is pretty trivially in 2QJ. Now I can use countable subadditivity. There's no reason why 2 times QJ are necessarily disjoint, but we don't care. We use countable subadditivity, and M is Lebesgue measure. Okay. Well, what's the measure of 2QJ? 2QJ is QJ, but twice the side length. So the measure of 2QJ, well, Lebesgue measure is the length of an interval. Let me move that over a bit. Okay. Well, the length of 2QJ by definition is the length of QJ times 2. So we can factor out this 2 here. But this length here, the sum of these lengths is, this whole thing is less than or equal to 4 over lambda And so this is 8 over lambda times the L1 norm of F. Okay, and that finishes the proof. So next time we will apply this to the Lebesgue differentiation theorem. And I just want to kind of show you what we're really going to prove, which is kind of interesting. Might be surprising, might not be, that we have to do a lot of, this is not easy to prove, but what we're going to prove is actually that for an L1 function, if big F is this indefinite integral, which is perfectly well defined, then this is not differentiable everywhere, but we can at least say for almost every x and r, big F is differentiable. And this could also be plus or minus infinity. Well, yes, plus infinity doesn't make sense. This could be minus infinity also. But yeah, for almost every x, big F is differentiable and F prime is F. Okay. All right, well, that's for next time. So long, take care, and yeah. Hopefully you slogged through this without too much difficulty. This is definitely more technical than what we've done before, but it's really just the nature of the beast. And, it is what it is. I mean, I find technicalities with dyadic intervals rather, interesting. They're often a pain in the ass to prove, but everything just works together so beautifully, in my opinion. But anyway, all right, so long, take care, enough of that.